t cosine beta t. So I have to pick on people who don't have their name tags then. What's your name, sir? Josh. All right, Josh. So can you give me minus integral voodoo now? However you see it.
Okay, the negative 1 over beta before the integral.
Okay. And there's a minus in the formula, right?
Yeah.
And then you're going to pull out the negative 1 over beta. So do you want me to change it to a plus now?
Can we put it before the negative?
Well, the formula has a negative, right?
Oh, okay. So
And you're saying you're going to pull a negative 1 over beta out?
it'll change the entirety of it?
It'll change everything to a plus, yes.
Okay.
You want to do that? Plus 1 over beta. Integral still. Okay, keep going.
And then cosine beta t. And then
That's it. Bracket closed, right? Because remember that bracket was right here? Good. Next line. Well, maybe before I do the next line, I should look at what I have here. My original integral, which I couldn't do. I've got a bunch of functions. I've got a new integral. I'm hoping I can do that. Can I do that? Yes, it's just cosine beta t. That I should be able to take the antiderivative of. See, I've eliminated the t. That was causing a problem. But it required two applications of integration by parts. So I have 1 over beta t squared sine beta t minus 2 over beta bracket negative 1 over beta t cosine beta t. Okay, let's do this. Antiderivative of cosine beta t. Careful. Y'all are doing this a lot. Y'all are doing derivatives instead of antiderivatives, so be careful with that. The antiderivative of cosine is sine. So, but the 1 over beta is there. So 1 over beta sine beta t, but you had a 1 over beta. So 1 over beta times 1 over beta is 1 over beta squared. Sine beta t. Yes? Plus c, right? Plus c. Now, what I'm going to do is I'm going to put a plus c on the very outside. And sometimes people are like, well, wait a minute. That c belongs in the brackets. And then this negative 2 over beta has to distribute, and it has to hit that c. But isn't negative 2 over beta times a constant still a constant? So does it matter what I call it? It's still some constant. So we just can always throw the c on the very end. Doesn't matter. One more line. I'm going to distribute this negative 2 over beta through, and I'll be done. 1 over beta t squared sine beta t. Then what? 2 over beta squared. It's going to be positive because negative times negative is positive. Positive 2 over beta squared t cosine beta t. And then I distribute here to here, negative 2 over beta cubed sine beta t plus a constant of integration. As the world turns, keeps going. So I've got a lot of interesting things going on this week that have had an impact on my availability. So let me try and run through this real quick. Today after class, I'm not available. Next Tuesday before class, I'm not available. So it's just some things that I have going on that are conflicting with my office hours. So I apologize. I would be happy to make up that time. On Fridays, I'm here normally. So if you want to make an appointment, you can. But just FYI. Okay, this should be it for this semester. These should be the only times that I have something going on. All right. Yeah, we're done. C. What'd y'all think of that one now?
That was ugly.
That was ugly? All right, there's a good opinion. See, that's why I'm looking for honesty. We can always count on Kiki for honesty. Why does it look like when you take the derivative it wouldn't?
Like if you were to check it, why does it look like it wouldn't?
Because that's how complicated the product rule is in chain rules, that when you do them, right, you get all these things happening. What's cool is, I mean, check it. You should just, on a piece of paper, just write it out. Take the derivative, and it's miraculously, it is going to all simplify to be that expression. All right, the next one, D. This one I called the rabbit out of a hat integration by parts. So when you say rabbit out of a hat, you think of a magician, right? Magicians like to pull rabbits out of hats. So this is somewhat of a magician problem, and one of my favorite examples. Because we're going to do something here that's very unnatural, but very cool. So let's see if we can foresee into the future with the red marker. First, this is integration by parts, because no basic substitution is going to help you here, right? Pick one of these to be u, the derivative of it's not there, you're kind of screwed. So you got to choose one of these to be u and one of them to be dv, and then try and imagine the new integral. So somebody give me one possible scenario for the new integral, and then someone else will give me the other possible scenario. So what's one possible scenario I could have here? I could have 2e to the 2x, so that would be if you choose this one to be u, right? And then what would the dv turn into over here? Sine x, right? And then I'd have dx. Right? That's what would happen if you let this be u and this be dv. The derivative of that's over there, the integral of that's there. Yes? Okay, let's compare that. What if we did it the other way around? Let the cosine be the u. Then what am I going to have over here? Negative sine x, and then I need to integrate this, right? Go antiderivative. So what's the antiderivative of e to the 2x? 1/2 e to the 2x dx. Understand? Those are the two things I'm foreseeing in the future here as being possible integrals. And I think you would agree they equally suck, right? They both have e to the 2x. They both have sine x. E to the 2x sine x. They both have constants that I can pull out, but other than that, they're the exact same thing, aren't they? I think you could argue neither one of those is better than the other, right? So what do we do? I mean, just you got to go with something, right? You got to try something.
Keep both.
Yeah, both.
Yeah, do them both. No, you have to pick one or the other. You can't do them simultaneously. All right, so let's see this. This is your first time seeing this, so let's see what happens. The bad thing is, like in the previous problem, we knew that t squared, if we repeated, eventually we could take the t squared down, couldn't we? T squared then became a t and then became a constant. Here, these are both, you can almost say that these are almost like cyclical, because the derivative of e to the 2x is always going to be itself, 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 itself. So no matter what I do, I'm never going to kill it off, right? And then with cosine, no matter what I do, it's just going to go back and forth between sine and cosine.
E to the 2x, you could do it like once or twice, so you get 2 as a constant, and then if you use 2x as u, then you have the 2 for the derivative when you try to integrate it back.
Well, let's see. You're saying choose that for you, and
Yeah, so like if you take to the derivative of e to the 2x first, and then you get 2 times e to the 2x, and then you take the integrand of that afterwards, and then you have the 2 for if you replace it with u.
all right, I'm going to have to see what you're saying in order for me to follow it. But I think you're saying let's let u be this one, right? E to the 2x. And let's let dv be the other one. We already know. We already wrote down what we think this is going to become. And we looked at it and said, I don't know, right? Du would be 2e to the 2x dx. And the antiderivative here we said was sine x. New, yes.
Well,
No, go, come on. No.
I was thinking the other way around. I'll let each of the two x be dv, but that's going to be a problem in itself.
What, e to the 2x, integrating it?
Yeah.
Well, we did that, didn't we?
Yeah, like,
That's e to a linear expression, so we should be able to integrate that.
yeah. That's what I was thinking about doing, because we did kind of the same thing except once we solve this, then we'd have uv, and then the du would be 2 to the...
Okay, so hold on, I'm going to write down. So, but you want me to stay with this, or you want to go to the other one?
Stay with that.
Okay, let's stay with this. So this is going to become, you're saying u times v, so those two together?
Yeah.
E to the 2x sine x. Everyone okay with that? That's just ultraviolet. Minus integral voodoo, which is this times this. May I pull the 2 out? Yes? The 2, right? That 2 right there is a constant. I can just pull it out. And then what's still in the integral?
Sine x.
Sine x times e to the 2x. Is that all right if I just write it like this again? Put the exponential function in front of the trig function? Okay, so we have this. Okay, now proceed.
And now I was thinking like we do it again.
We do it again?
Except we switch them.
Okay, so this is a very good thing you brought up. If we do this integration by parts again, but we switch the order, pay attention. That means instead of letting u be this one, we let u be the other one, right? So I'm going to write this table down. I'm going to write it in red, but this time the red means danger, okay? So if I look at this integral and I let u be e to the 2x, no, you said switch it, right? You said switch it. Let this be the sine x, and this one be e to the 2x, right? Then you're going to differentiate down, aren't you? Integrate back up. But isn't that exactly what you did here backwards?
Yeah, but I was thinking about
Right.
doing it with 2 times e to the 2x.
Yeah, the constant's not going to, the constant won't do it. Look, this is a rabbit out of the hat problem. You got to see it the first time. Because it's, what happens here is really neat, but you got to see it happen, all right? Like, let me show you what's going to come of this. Right now, do we all agree we're still kind of stuck? We're almost equally as stuck as we were to begin with. The only difference is we have a sine instead of a cosine. Okay, I'm going to set up integration by parts again, and I'm going to do the exact same substitution. Watch what happens. So same, I'm just working on this right now, right? What's in brackets is what I'm about to work with. I'll create a new table over here. My new table, I'm going to make the same exact substitution. U is equal to e to the 2x. dv is the sine x dx. All right. du is, we've already done this, haven't we? 2e to the 2x dx. And what's v? Negative cosine x. All right. Let's see, who have I not picked on? Ivana, I haven't picked on you today. You look like you're following, so I'm going to let you, let's see. I'm going to write this first part out for you. Here's the 2, and then my brackets. And then if you could, please, let's get our, what goes in here?
Negative e to the 2x.
So you're putting these two together. You put the negative out front. I'm okay with that. Negative e to the 2x cosine x.
And
2e to the 2x.
oh,
What do you want me to do with the sign here? Because we have an integral, right?
minus the,
You want to do minus integral here, and then what goes in here?
you can put the 2 on the outside.
2 on the outside?
Yeah.
We're talking about this 2 right here? What do you want me to do with that?
Oh, I can go out there.
You want me to bring that out there? You want me to change that to a plus?
Yes.
Okay. All right, so continue. What's in here?
E to the 2x
E to the 2x
cosine
cosine x
x.
dx. Everyone agree? Yes? All right, so what we're saying is this. This integral, e to the 2x cosine dx, is equal to this, and then the minus 2 distributed through, and then this integral. Can you handle this integral? No, because that's this integral, isn't it? So you're right back where you started. You have the original integral you're trying to find. You've got it actually in terms of itself. And this actually is what you want. Okay? This is actually going to be a very nice thing. So watch what happens. This is the rabbit out of the hat. Well, actually, there's the rabbit. Okay? We can see its ears. Now we got to pull it out of the hat. Okay? So look, what we're trying to solve for has appeared over there. Yes? So what I'm going to do is I'm going to rewrite this integral. Like the left side is here, right? This is the original problem. We're saying it's equal to this. I'm going to rewrite that. And I'm going to distribute everything through to get rid of my brackets right now. So I'm going to say this part right here, e to the 2x sine x. Now distribute a negative 2 through here and through here. And what would you get? Here? Plus 2e to the 2x cosine x, right? That's this times this. And then what's this times this? Minus 4 integral e to the 2x cosine x dx. Yeah? You're smiling, Ethan?
Yeah.
You know what I'm going to do? What am I going to do?
With algebra,
Yeah, this is just algebra now. Yes, what am I going to do, Ethan?
you're going to pull the negative 4 integral out to the other side.
How do I do that? If I'm subtracting 4 of them,
You're going to add the 4 times.
I'm going to add 4 of these integrals to both sides of the equation. That's what I'm going to do. See, what I'm trying to solve for, good, Ethan. Not a lot of people see that. So I'm going to algebraically realize that what I'm trying to solve for is appearing over there, and so I can add 4 of these integrals. I don't know what they are, but it's a balance, right? I can do the same thing to both sides. So I can add this integral, whatever the hell it is, to both sides of the equation. What happens over here? It's gone. And over here, if you have one of these integrals and you add 4 of them, you will have how many of them? 5 of them. So 5 of these integrals will be equal to just these 2 pieces right here, right? Just these 2. E to the 2x sine x plus 2 e to the 2x cosine x, right? And all that went away. But that's what 5 of those are. I don't want 5 of them. How many do I want? 1. So how do I get rid of that 5? Divide both sides by 5. Or multiply both sides by 1/5. Either way, however we want to look at that. So if I multiply both sides of this by 1/5, I'm going to get the next line. Can I erase what's up on top? All right. So multiplying the left side by 1/5, I get integral e to the 2x cosine x dx. Multiplying this times 1/5, I get 1/5 e to the 2x sine x. And multiplying this times 1/5, I get plus 2/5 e to the 2x cosine x. And then there's something missing. Who said that? Christy, you remembered it. Okay. This rabbit out of the hat thing, you kind of never really take an integral. Like you do the integration by parts, but like you actually never get an integral at the end that you integrate and get plus c, because you move that integral to the other side. But we know that this is the antiderivative, and so we need to tack the c on, because this should be a family of functions. We okay? Now, Zach, I'm going to take derivative of this because I think you've brought up a question. You're a little skeptical as to whether or not this was working, right? So my claim is that, okay, there. My claim is that if you take the derivative of this, oh, I forgot to put the plus c up here. I put it on the bottom, sorry. If I take the derivative of this right side, I should get the integrand. Yes? So let's see if you can keep up with my derivative. I'm about to take derivative of this right here. What do I have to use right here? Product rule. Okay, derivative of the first piece. Derivative of e to itself, or e to 2x is itself, times 2, right? But there was a 1/5 out front, so 2/5. That's the derivative of this. Times the second one, plus derivative of the second one. What's the derivative of this? Cosine x times the first one. Okay, I'm done with that. Plus, now derivative of this, another product rule. What's the derivative of e to the 2x times 2/5? 4/5 e to the 2x times cosine x. Plus, now derivative of cosine x. Negative sine x times e to the 2x times 2/5. Sorry, I forgot the 2/5 there. Yes? I think these cancel. Don't they? Those are exactly the same except positive and then negative. This is 1/5 of these, and this is 4/5 of these. That's 5/5. That's 1. So my answer should just be one of those. That's the integrand. Right? It works. Okay? It works. It's quite beautiful if you think about it. I mean, it's a way to go backwards. It really is. It's almost a product rule for integration. It's almost that. Right? Except that it is a product rule for integration. If you have a product, it turns into this. The downside is that your right side includes another integral, which you either can or cannot do. So, all right. Still have 10 minutes. I still have 2 examples. All right, so the next one. Integral e to the square root of x dx. Is that it? Man. This will be our last one for the day. Sorry we couldn't do any like group work or like, hang out and chat and stuff, that I just had to do examples all day, but you got to see this stuff first before you can. I mean, can you imagine I give you a problem like that last one and be like, yeah, go figure it out. Like no one ever showed you anything like it? Be pretty tough, right? There's the formula. Now go figure it out. All right, so this one, I give you a hint in this problem, right? I give you a hint, but if I didn't give you that hint, then you would look at this and you'd be like, basic substitution. Do you see something in its derivative? Not really, right? So you start thinking, okay, well, integration by parts is the only thing I have. I have to choose something to be u and dv, but there's really only one choice for u here. What is it? This whole thing, right? So let's just write down what that would be, and then we're going to realize that this is going to become pretty ugly. So I'm going to write it down. My only choice right now is let u be e to the root x. And dv then by default has to be the what? Dx. And then that means when I go up to v, I've got x. And then over here, I've got a derivative. Okay. du is derivative of e to anything is itself times the derivative of what's up there, 1 over 2 root x dx. Now look at that new integral that you're going to have, which will always be this diagonal, won't it? You're going to have an e to the root x, which you had already, right? But now you've introduced this root x on the bottom. You're going to multiply times x. What is x divided by root x? Just x divided by root x. Just root x. So your new integral is going to have a root x times e to the root x, which is worse than this. Isn't it? So,
Professor?
Yes.
Should it also bring the power down? Like, it can also have the same thing.
Bring the what now?
No, if we bring the power down, like, yeah.
Only if there was a natural log.
Oh.
I think that's what you're thinking. The property of the natural log is you can pull the power out. If we had a log, we could. And we can't introduce a log because this isn't like an equation where you can do log on both sides or anything. So we're kind of stuck. OK, so this doesn't look like it's going to work because my new integral seems tough. So going to make a very unnatural substitution to start the problem. And like I said, it's one of those things where you see it that first time and you're like, OK, sure. All right. I'm just going to say u is root x. All right, what's du? It's 1 over 2 root x dx, isn't it? Now, we said we don't have its derivative here, do we? We don't have the derivative of root x here anywhere? You all agree with that? So I know I can rewrite this e to the u, right? But dx, how can I rewrite dx? I have to get it to match up. So I have to isolate this, don't I? How do I isolate this? Take that to the other side, right? Multiply both sides by 2 root x. So it's going to be 2 root x du equals dx. Do you follow this? Now this I've never done before, and you should probably be asking yourself, what are we going to do about this? Because we have x's mixed with u's, don't we? I'm going to replace dx in this problem with stuff with u's and x's. Yeah? And that we've said we want to avoid. But does anyone see what I can do with root x? What is root x? It's u. No, root x is just u. Just coincidentally, isn't it? So isn't this just 2u du? Isn't that what that is? Isn't that all it is? 2u du? So let me try and rewrite the problem then, because I'm almost out of time. Let me try and rewrite this problem. This becomes integral. What did we say e to this was? E to the u. And what are we saying that dx is? 2u du? Yeah? That's what it is. Questions? Can I pull a 2 out? Is that all right? So this becomes 2 integral u e to the u du. U e to the u du. Do we agree?
Yes.
How are you going to do that integral? Integration by parts. Because now we do have 2 things, don't we? And you can choose one of them to be u. Wait a minute, we're already using u. So we won't be able to use u, will we? But we will be able to choose one of these, and then in the new integral, it'll be the derivative of that, won't it? And then the other one will be our dv, and in the new integral, it'll be the antiderivative. So I need to set up an integration by parts table. I'm still going to call this dv, but do you see why I can't call this u? I'm already using u. So let's use a different variable. Doesn't matter. W. So w is the u. dv is the everything else that was left, e to the u du. And then work your table. Derivative down on this side. dw is du. Oh, yeah, right? And then up here, v is e to the u. Let's see, who have I not called on? Karen, I don't call on you very often, right? Yeah, I do, or no, I don't?
You don't.
I don't. Okay, so I'll let you do this. I know you've been dying to. All right, so the 2 here, right? And then I want to use integration by parts using this table. So there's the 2. I'll even put it in brackets for you. Give me the, we can't say ultraviolet anymore, right?
So it's going to be u, e to the u.
E to the u. Go ahead.
Minus the integral.
Minus the integral.
Yeah. U to the e to the u dt.
E to the u du. That's it. So we're still doing like the ultraviolet minus integral voodoo, but do you see now it's more important to understand the pattern than it is to understand the letters? And then, do we know the antiderivative of e to the u? It's itself, right? So I'm going to distribute the 2 through. 2u e to the u minus, distribute the 2, and then antiderivative of e to the u is itself. E to the u plus some constant of integration. Boy, that looks terrible. What was u? Square root of x. So the final answer should be equal to 2 root x e to the root x minus 2 e to the root x plus c. Of course that's the antiderivative of e to the root x. Of course. Right? I mean, if you're having trouble seeing that, then you got problems, right? I mean, that's... Okay, so everyone follow me on this? All right. We have about a minute and a half. I want to show you one more thing on this same exact problem. I want to show you something I haven't shown you. This was the original setup of the problem. We made a substitution that I said wasn't very natural, right? Right here. And it worked, didn't it? It actually worked, but it required a little bit of massaging, and we got it to happen. So normally what we would do here is just take derivative of both sides, wouldn't we? Du, take derivative. Now, just tell me if you agree. Is this true? Just square both sides? Now what I'd like for you to do is take the derivative implicitly. So what's the derivative of u squared? 2u times the derivative of u, right? What's the derivative of x? dx. Now go back in your notes. Didn't I write this line down somewhere? Didn't I? We actually had this. We had 2 root x du equals dx. And I said, hey, but what is root x? I said it was u, and we replaced the u, and we wrote that down, didn't we? Do you see that if you have an equation, you can take the derivative now, but you can also do some stuff algebraically and then take the derivative. So just be aware of that. You're free to do that in a problem. See, I got an expression for dx in terms of u explicitly right here by doing this step first. Well, I don't know where the time goes. We still have another example, and our schedule, we were supposed to have started this today. Okay, so that's why I got a little bit ahead, so that we could have a little time for this. So on Thursday, right, September 10th, Thursday, we'll be doing more integration by parts. But what I really want to be able to do is kind of give you problems to work, right? So let's see. I mean, I think maybe the first half hour, I'll give you some integrals to work on, just as practice. And then we'll start getting into, we need to talk about an exam. We're supposed to have an exam, not this Thursday, but the following Thursday. And I think you want this exam, but I think you do, because most Cal 2 classes, their first exam doesn't come until after they've covered all the techniques of integration, which is very difficult because then your integrals can be anything. Like, it can be one of 5 techniques. If I give you this exam next Thursday, you know you basically can have U substitution, integration by parts, and that's it. That's all you can get, which really narrows it down. And some faculty would argue that that's not ethical to have some classes doing it this way and others doing another way. But it's the way that my schedule worked out. That's the way I'm doing it. So attendance, let me do that real quick. Oh, you know what? Did anyone not take the quiz? Okay, then I'll take attendance off the quiz. You're free to go. Do your homework, which is on this, which I'm putting on the board. And I mean this, do your homework, all right? This is a lot of problems. Page 316, 1 through 32, 35 and 37. You can do 1 through 32. I've shown you everything you need to do 1 through 32. 35 and 37, those might take a little more effort.